Okay, we're going to pick up where we left off with mixtures. Mixtures, like we said, is composed of more than one substance. It can have varying composition. It can be any combination of solid, liquid, and gas. And you can separate it by a physical change. So sugar and water is a mixture. You can separate it by evaporating the water. Oh, let's try this one. Element versus a compound. An element is a pure substance that cannot be broken down by any chemical reaction. So we have the periodic table of elements. You can't break them down. So now you cannot change lead into gold. A compound is a pure substance formed by chemically joining two or more elements. We can take sodium, which is a metal, highly reactive, toxic. React it with chlorine, which is a highly toxic gas, and end up with sodium chloride, a compound, normal table salt. Baking soda, sodium, hydrogen, carbon, and oxygen, all combined in a certain ratio to give us a compound. So if we look at sort of a flow chart and classification of matter, can it be separated by a physical process? If so, it's a mixture. And remember, we have two types of mixtures: homogeneous, evenly blended; heterogeneous, not evenly blended. So air is what kind of mixture? Homogeneous or heterogeneous? Sure? So air is a mixture. We have nitrogen, oxygen, argon, water vapor, carbon dioxide. Well, it better be homogeneous, because I don't want to be standing here and have 28% oxygen and be talking to you, and then come over here and have 2% oxygen and fall over dead. That would not be a good thing. So it better be homogeneous. If we can't separate it by a physical process, we have a pure substance. Can we perform some chemical operation on it and break it down even further? Then we have a compound. If we can't break it down further using a chemical process, we have an element. That's kind of a flow chart on what's going on. Now let's talk about measurements. Now we're going to get into some of the math. A measurement, and this is a key point, is composed of a number and a unit. Without a unit, the number is meaningless. I told you before, my daughter's a nurse, medical ICU at Duke. Her first week on the job, she came home and she's walking kind of stiffly. She says, "My back hurts. I hurt my back at work." I says, "How'd you do that?" She says, "Moving a patient." She says, "The patient weighed 200. My daughter was kind of athletic. She played softball and volleyball in high school, and she did all kinds of work out in the gym. Because 200 is not a lot. I mean, it's not light, but it's not a lot to be moving. She says, "No, Dad, 200 kilograms. 200 kilograms is 440 pounds. So without that unit, that number was meaningless. I was thinking pounds. She meant kilograms. So the unit is critical. You're a nurse, the doctor comes in and says, "Quick, give that patient 5 insulin." 5 what? 5 milliliters? 5 liters? Heck of a lot of insulin, but you don't know what to give without the unit. So whenever you do a measurement, you have to have a unit. It has to be the proper unit. A number of years ago, there was a Mars probe where they were going to, a little thing comes into Mars, and they had these balloons that deploy, and it kind of bounces along the surface. First one they sent came in, hit, smashed into smithereens. several $1 billion worth of equipment gone. They looked at why they did it. Well, they subcontracted the calculations for the entry into Mars to a company in England. They did all the calculations, sent the numbers to the U.S., who put them into the program. The company in the UK did the calculations in metric. The program written in the U.S. were English units. So everything was off by several factors. So it came in a lot faster than it should have, and of course it just exploded when it hit the planet. So looking at this page for this baby, weight. If I said 3.9, you go, wow, that's a premature baby. And you're thinking pounds. 3.9 kilograms, which is 8 pounds, 8 ounces. That's a nice, healthy baby. If I said the baby was 53.3, you go, wow, that baby was over 4 feet long. No, we're not talking that. We're talking 21 inches. So without the unit, the number is meaningless. So make sure you get in the habit when you give numbers that you give units. Proper aspirin dosage. 325. Do you want to take 325 milligrams or pounds? Well, I'm sure that 325 pounds to get rid of your headache, but a fast time for the 100-meter dash. 10.00 seconds or days. Olympic athletes' time, my time. Okay? The English system, which we use, uses units like miles, gallons, pounds. The metric system uses units like meters, liters, grams. We're going to be using the metric system. Because it's easy to convert in the metric system. It's difficult to convert in the English system. Because you got to go from, if I say inches, how many miles? Well, then you got to go from inches to feet to yards to miles. It's 12 inches to a foot, 3 feet to a yard, 5,280 yards to a mile. So what are the units in the metric system? Length, the base unit is meter, small m. Mass, base unit is the gram, small g. Volume is the liter, capital L. Time is the second, small s. So you're familiar with all those terms. Prefixes, and you should be familiar with some of them, especially if you deal with computers or if you bought a computer recently. Giga is a billion. So, in computers, your hard drive is so many gigabytes. Mega is a million. Kilo is 1,000. I know you've heard the term kilo. Deci means a tenth. Centi is 100. So there's 100 centimeters in a meter. Think of centipede, 100 legs. Milli is 1,000. Okay, if you think a millipede supposedly has 1,000 legs, there's 1,000 millimeters in a meter. Micro is a million.
Yeah, that symbol I hadn't recognized before.
Micro?
That symbol.
The symbol, that little U.
Yeah.
And nano is a billion, 10 to the minus 9. So that's really not a U, it's a lower case Greek letter for mu. So for measuring length, 1,000 meters is a kilometer. Or 1 meter is 1/1000th of a kilometer. So you see kilometers all the time when you get in your car. That's the other part of the speedometer. Thank you. There's 100 centimeters in a meter, or 1 meter is 1/100th of a centimeter. Or 1 centimeter is 1/100th of a meter, rather. So basically, all you're doing is multiplying or dividing by a factor of 10. 1,000 millimeters in a meter, or a millimeter is 1/1000th of a meter. And it takes practice, but you'll find that the more you do it, the easier it becomes. Pretty much like anything you're going to do. So mass is the measure of the amount of matter in an object. It is different than weight. Weight is the force that matter feels due to gravity. So if you have any mass of 120 kilograms, and you get on a scale here, it'll say 120 kilograms. If you go to the moon, you get on the scale, the moon has 1/6 the gravity, the scale will say 20 kilograms. But your mass is still 120 kilograms. Because the scale registers the effect of gravity. If we were in a lab, you wouldn't be using a scale to weigh stuff, you use a balance. So, in the old days, a balance was actually a balance, like a teeter-totter. Now you'd put a reference weight, say 1 kilogram on here, and what you're weighing on the other side, and if it perfectly balanced, this would be 1 kilogram. So even if you went to the moon, and you took this apparatus out, you put a 1 kilogram reference here, and you put yours, it's still 1 kilogram. The scale is different. Scale has springs, and it's the effect of gravity pulling on the springs. Volume, again, is the liters, and again, we're looking at the same conversions. Kiloliter is 1,000, 1,000 millimeters in a liter. Volume, going back to doing a little geometry here, volume of a cube is the length times the width times the height. So if we have a cube, here you get to see why I didn't go in the arc. We have a cube, 1 centimeter on an edge. We multiply them all together. 1 cubic centimeter. See it written this way. You also see the abbreviation cubic centimeter, cc. A cubic centimeter is equal to 1 cubic centimeter is 1 milliliter. In the health profession, you use cc's a lot. So if the doctor comes and says, give this patient 5 cc's, and you happen to pick up a syringe that's marked in milliliters, don't panic. It's 5 milliliters. It's the same number. If you're in a doctor's office and the nurse says, wait a minute, I got to convert cc's to milliliters, ask for a different nurse. English metric equalities. I'm not a big fan of going back and forth, but we can. But just to give you some idea of what's going on, 1 inch is 2.54 centimeters. A meter is 39.4 inches. So a meter stick is a little bit longer than a yardstick. So if you get a meter stick and a yardstick, the yard will have 36 inches, the meter side will have 39.4. A kilometer is a little over half a mile. A kilogram is 2.2 pounds. And 454 grams per pound. Let's see what some other ones you might use. A liter is a little bit over a quart. So you have 2 liters of Pepsi, you got actually 2.12 quarts. So if you happen to go to Canada to get gas, your gas pumps are liters, as opposed to gallons, and then there's imperial gallons, which are different than U.S. gallons. You can never figure out how much you're paying for gas. Significant figures. What makes a figure significant? Whenever you do a measurement, there is uncertainty. Rulers, yardsticks aren't calibrated, balances are not calibrated. You know darn well you can get on your bathroom scale at home and have one weight, and you go to the doctor's office and get on their scale, and it's completely different. I don't know what the doctors do, but it's always heavier at the doctor's office. Okay. So let's talk about exact number. An exact number is a number that results from counting or is a definition. So if I ask you to bring me a dozen donuts, how many are you going to bring me? 12. Exactly 12. Unless you ask me, then you may end up with 10 because I ate 2 on the way. But no, a dozen is exactly 12. We're not talking about finger stuff. Okay. I knew somebody was going to say that. I count the people in this room. 32. There's exactly 32 people in this room. There's not 31 and a half people. And there's not 32.2 people. Don't say it. What if you're pregnant? No, we're not going to do that. Okay. Or by definition. 1 foot is how many inches? Exactly 12. It's not 11.5, it's not 12.2. So those are exact numbers. An inexact number results from a measurement or observation that contains some uncertainty. You take a ruler, you measure your book, and you say it's 25.2 centimeters. There's some uncertainty. I could hand everybody a ruler, you could all measure your books, and I'm sure we would get some different answers. They'd all be close, but there'd be a little bit of difference in there. So here, we're measuring this fish using 2 rulers. If we look at the top ruler, we can see that the fish is at least 50 centimeters long. We know it's at least 50 centimeters. And we know it's less than 60. In between, we have to estimate. Now, depending on where you're sitting in the room and what view you got, we can look at it. They say it's 53. You might say it's 54 or 52. We have 53. The bottom ruler, which has more accurate markings, we know it's at least 53. And it's less than 54. So it's somewhere between the two. Again, you're making an estimate. You say it's 53.5. Which one is more accurate? Okay, you're going to the doctor, you're going to get LASIK surgery, you're going to hit your eye with a laser. Which ruler do you want them to use? Bottom one. I'd ask for even a more accurate one too, but. So, how do we figure out the significant figures? If we look at the top one, we know the 5, we estimated the 3. That has 2 significant figures. The bottom one, we know the 5, we know the 3, and we're estimating the last 5. That has 3 significant figures. When you look at a number, it's the number. The significant figures are all the ones you're certain of, plus the estimated one. Now there's some rules. Any number, all non-zero digits are significant. So if I look at 65.2, they're all non-zero, so there's 3 significant figures. It doesn't matter where the decimal point is. 255.345, they're all non-zero. It has 6 significant figures. If there's a 0 in the number, if it's surrounded between non-zero numbers, it's significant. So 29.05 is 4 significant figures. 1.0087 is 5 significant figures. If it comes at the end of a number, we call these trailing zeros. If there's a decimal point, they're significant. So 3.7500 has 5 significant figures. 620, and there's a decimal point there, has 3 significant figures. If it was just 620 without a decimal point, there would be 2 significant figures. If the 0 is at the beginning of a number, we call those leading zeros. It's never ever significant. So 0.00245 has 3 significant figures. 0.008 has 1 significant figure. If there's no decimal point, the ones at the end don't count. 2570 has 3 significant figures. 1245500 has 5 significant figures. Okay? So I'm going to stop this. Okay. Calculation rules. This is where people have problems too. When you multiply or divide your answer, okay, your answer has to have the same number of significant figures as the measurement with the least amount of significant figures. So for example, the top number here has 4 significant figures, 351.2. 5.5 has 2 significant figures. So you get out your little calculator, calculator says 63.854545. Do not give that as an answer. You need 2 significant figures, because that's the measurement with the least amount of significant figures. So you come over here, 2, 6, 3. Then you look at the next number. It's an 8. If it's 5 or above, you have to round that up. I mean, the rules of rounding that you've always had. So the answer should be 64. And 64. Your answer cannot be more accurate than your least accurate measurement. Does that make sense? You do a whole bunch of measurements, and you have one that's very inaccurate. It doesn't really matter how accurate the rest of them are. You can only be as accurate as your least accurate measurement. So here's some examples. 23.2 times 1.1. 3 significant figures, 2 significant figures. Your calculator shows 25.52, which is how many significant figures? 4. You got to have 2. So you look at this, 25. The next number is a 5, so you have to round up. Makes 26. Here we have 25.0, which is how many?
3.
0.50, which is 2. Calculator says 50. It's got to be 2 significant figures. This has got 1. So you put a 50 with a decimal point. There's another way to do it, which would be, I don't know why I didn't get the pen right. Scientific notation, I could put 5.2 times 10 to the first. Oh, I'm sorry, not 5.2. 5.0. So 5.0 has two significant figures. We'll talk about scientific notation in a little bit. Addition and subtraction. Your answer has to have the same number of places after the decimal point as your measurement with the least number. So it's different for addition and subtraction. So here I have 10.11, 2 decimal places, 3.61 decimal place. Due to subtraction 6.51, I have to go to just 1 decimal place, because this is 1 decimal place, I end up with 6.5. Okay? So let's try one. Scientific notation. Used a lot. Science is why it's called scientific notation. Consists of couple parts. We have a coefficient and an exponent. Coefficient is always a number between 1 and 10. The exponent can be any positive or negative whole number. How do we do this? Well, let's look at the first one, 2,500. How many significant figures? 2. Okay. When you look at scientific notation, your coefficient has to have the same number of significant figures. So I have to have 2 in the coefficient. We start where we understand the decimal point to be here on the end, and we move it to the left till we get a number between 1 and 10. So if I move it once, I have 250. That's not between 1 and 10. If I move it again, I have 25. That's not between 1 and 10. If I move it again, I got 2.5. That's between 1 and 10. So our coefficient becomes 2.5. How do we get the exponent? How many times did I move it? 3. Here's our exponent. What if I have, okay, let's do the 0.036. How many significant figures? 2. Again, I have to move the decimal point to get a number between 1 and 10. Well, here I know where the decimal point is because it's right here. I move it, now I'm moving it to the right. I move it once, I have 0.36. That's not between 1 and 10. I move it again, now I have 3.6. That's between 1 and 10. 3.6 times 10. I moved it twice, but I moved it twice to the right. So now it becomes negative. 3.6 times 10 to the minus 2. Okay? Next page is here. Stop. Recording back on. Okay, here we see some reasons to use scientific notation. The human body contains 2 times 10 to the 13th red blood cells. It's a lot easier writing this number than 2 followed by 13 zeros. I don't know about you, but I always have a hard time, even when I have to put an account number in a bill or that, and you got like 6 zeros, and I'm sitting there trying to put the account number on there. How many zeros I got to put on there, and I just end up short one or adding one. A single red blood cell has a diameter of 6 times 10 to the minus 6 meters. Very small number. So there's the bottom here, standard notation, 2 times 10 to the 13th. You can see how many zeros you have to write. And the diameter of the red blood cell, you can see how many zeros you have to put in there. After a while, it's tough to keep track of all the zeros. So that's why we use scientific notation. To go back, when the exponent is positive, you move the decimal point to the right, which we just did. Notice here, 2.800, 4 significant figures. We have to have 4 significant figures in our final answer. So we move it 2 places, that means it's 280.0. When the exponent is negative, you're going to move the decimal place to the left. 2.80, you have your imaginary zeros after that, becomes 0.082. 0.0280. So again, I urge you to go and practice those. It will become second nature. Yeah, after 30 years, I can do it. Really. I don't have 30 years. Okay. Now we're going to move into doing conversions. Problem solving using conversion factors. What is a conversion factor? It's a term that converts a quantity of one unit to a quantity in another unit. Conversion factors are usually written as equalities. 2.20 pounds is 1 kilogram. So that's an equality. We can then make a ratio or a fraction, change that equality to a fraction. We can say 2.2 pounds per kilogram, or the reciprocal, 1 kilogram per 2.2 pounds. And we're going to use what's called the factor label method, or you may have heard it referred to as dimensional analysis. Ooh, big scary words. Okay? The factor label method uses conversion factors to convert a quantity in one unit to a quantity in another unit. The units are treated like numbers. The units have to cancel. So, to convert 130 pounds into kilograms, we start with 130 pounds. Always put the units in there. We have to have some conversion factor to give us the kilograms. If we remember for the previous slide, we can have, here they use 2.21. Don't ask me why they changed it from 2.20. 2.21 pounds per kilogram, or 1 kilogram per 2.21 pounds. To get the pounds to cancel, you have to use the bottom one. Because this is in the numerator, this is in the denominator. So the pounds cancel. Now you do the math. 130 times 1 divided by 2.21, 59 kilograms. Remember, 2 significant figures. Because 130 only has 2 significant figures. Okay. Stop this. Okay, here's a problem. How many grams of aspirin are in a 325 milligram tablet? You can figure this out. I have confidence in you. 1 gram is equal to how many milligrams? 1,000. Go. Figure it out. here's another challenge. Do not use your calculators. It's in the book. I know it's in the book. Try doing it without the book. What are we starting with? 325 what? Always have the units. What do we want to end up with? Grams. So I have to multiply it by a conversion factor that has what in the top? Grams. What in the bottom? Milligrams. So what number goes in the top? The grams? What goes for milligrams? So now I have 325 divided by 1,000, which is 0.325. So don't use your calculators. You should know both. Divide by 1,000 with the decimal point over 3 spots. Okay, let's just see how they do it. There they go, 0.325. And if you look at the problem, you know, I always encourage people to think about what your answer should be. Which is bigger, a gram or a milligram? A gram. So your answer should be lower, a lower number than the milligram answer. So if you used the wrong conversion factor by mistake and you ended up with 325,000 grams, no, I got to have a number smaller. So you know you did something wrong. Always think about your answer. Make sure that it makes sense. Okay? But again, we can do it 2 or more conversion factors. It's a step-by-step process. We can do 2, 3, 4, 5, 6 steps. How many liters are in a pint of blood? We're starting with 1 pint. We want to know liters. We have two equalities. 2 pints is 1 quart. 1.06 quarts is 1 liter. That's what we're given. We can make conversion factors: 2 pints per quart, 1 quart for 2 pints. For the second equality, 1.06 quarts per liter, or 1 liter for 1.06 quarts. We can't go directly from pints to liters, so we weren't given an equality for that. So we can go from pints to quarts, then from quarts to liters. 2 steps. So we start off with pints times 1 quart for 2 pints. So these labels cancel. Quarts, we're going to liters. Quarts is on the top in the second. It goes on the bottom in the third. Going with the 1.06. You do the plug and chug in your calculator, and it'll spit out an answer. We need 2 significant figures. These, the 1 quart over 2 pints, those are exact numbers. So they have an infinite number of significant figures. You don't use those in the calculation. 0.47 liters. So just like we did going from quarters to nickels, it's the same process. Use the labels. So, here we're doing a little bit of clinical work. A patient is prescribed 1.25 grams of amoxicillin, which is available in 250 milligram tablets. How many tablets are needed? Well, we start off with 1.25 grams. We have to know how many tablets. A tablet contains 250 milligrams. So we have to know how many milligrams we have to start with. We have to take the 1.25, convert it to milligrams, 1,000 over 1, then divide it by 250. If you do that, you find out you need 5 tablets. I think if you actually do the calculation, no, it comes out exactly 5. But if it came out to be 4.7, you can't get 0.7 for tablet, you get 5 tablets. All right. We've been converting mass, length, all kinds of things. Now temperature. Temperature is a measure of how hot or cold an object is. Most people are used to the Fahrenheit scale. That's what you get in the weather report. Chemistry, nursing, doesn't use Fahrenheit, they use Celsius. Chemistry also uses Kelvin. Notice Fahrenheit and Celsius have a degree symbol. So it's degrees Fahrenheit, degrees Celsius. Kelvin does not have a degrees symbol, it's just a K. Oh, you haven't heard of that? Okay. Kelvin scale is temperature related to actually molecular motion. And we'll use that later on when we study molecular motion and thermodynamics. So to go from Celsius to Fahrenheit, you take Celsius temperature multiplied by 1.8, add 32. To go from Fahrenheit to Celsius, you take the Fahrenheit temperature, subtract 32, and divide by 1.8. To go from Celsius to Kelvin, you take the Celsius temperature and add 273. So the freezing point of water is 0 degrees Celsius, 273 Kelvin. There's no place I can stand it. And to go from Kelvin to Celsius, you take the Kelvin temperature and subtract 273. So absolute 0 is the coldest it can ever be, where all atomic motion stops. So absolute 0 Kelvin is negative 273 Celsius. That's cold. So let's try a problem. I don't want to do anymore. Real quick. Minus 40 degrees Celsius, what's its temperature in degrees Fahrenheit? To go from Celsius to Fahrenheit. You use your calculators. Your calculators. What'd you get?
Okay, right.
What'd you get? Great, it's not right. Anybody else? Nope. Anybody else? How do you go from Celsius to Fahrenheit? Take the Celsius, multiply it by 1.8, and add 32.
40.
You know what?
It says negative 40.
It says negative 40.
Yeah.
This is negative 40.
I know.
40. Oh, negative 40.
Oh, yeah, it is.
Well, I won't keep you in suspense. The answer is negative 40.
Yeah, I know.
Negative 40 is the one spot on both scales that they intersect. It's the one spot where they're both the same answer. I just put that out there for most people do the calculation. Go, it can't be right because they got negative 40. But,
Now, how did you get it again?
Pardon?
How do you do that again? You did 55 or added by 1.8?
You're going from Celsius to Fahrenheit. So it's minus 40 times 1.8 plus 32. Okay?
By 1.8.
Yeah.
No, you multiply it.
will be later for me. So it's a possible